Today we want to build a molecular orbital diagram for a second period diatomic molecule. First, we create a scale for the diagram. Energy will increase as we go up, so the higher something is on the chart, the more energy it has. We have three electron configurations to document. The first two are the original electron configurations of the two independent atoms in their ground state. These will contain one s orbital for each energy level and three p orbitals for the second energy level. We'll use box notation to hold the electron spin arrows for each electron. Now we build the molecular bonding orbitals. For the first energy level, we have a sigma bonding and a sigma antibonding orbital. Each atom can contribute electrons to each level, starting with the lowest energy level. We add a similar bonding and antibonding molecular orbital pair for the electrons from the level 2 s orbitals. Now we build out the molecular orbitals for electrons from the two p orbitals. Electrons from p orbitals can form both sigma bonds along the axis between the atoms and one or two pi bonds from pi orbitals that reform around this axis. So we have 6 possible molecular orbitals, 3 lower energy bonding orbitals and 3 higher energy antibonding orbitals. Now that we have our grid in place, we can start to see how valence electrons can form bonds explained by the molecular orbital theory. The simplest diatomic molecule involves 2 hydrogen atoms, each sharing their single 1s electron. By the rules of molecular orbital theory, available electrons move first into the lower bonding sigma orbital. The electrons in the bonding orbital occupy a lower energy state than they did originally, so the bond forms. For helium, we have a different story. 2 electrons move into the bonding orbital, but the remaining 2 electrons need to occupy a higher energy level antibonding orbital if the molecule forms, so helium will not form a diatomic molecule. Now we consider oxygen with 8 electrons. First, we populate the valence electron orbitals for the oxygen ground state, and following Hund's rule, the 2p electrons spread out into the 3 available orbitals. Following the rules of molecular orbital theory, we move electrons into the available molecular orbitals, starting with the lowest energy levels. S electrons on both energy levels create both bonding and antibonding pairs. The final 2 p electrons occupy separate antibonding p orbitals, another example of Hund's rule. Oxygen has 10 electrons in bonding orbitals and only 6 in antibonding orbitals. So the bonding attractive force is strong enough to overcome antibonding forces. The diatomic oxygen molecule will form.